Ben is going to be presenting on a readily interpretable, fully convolutional autoencoder-like model for unlabeled waveform analysis. It's my favorite title in the sessions. Okay, go ahead, Chris. I mean, Ben.
Thanks, Scott. Yes, it is a catchy or a mouthful of a title. I'm a postdoc at the University of Bristol. I work on the LZE experiments, and there's a team of us that have been sort of involved in this. Like, I want to highlight that a lot of the work I will show here has been done by project students over the last sort of few months, 6 months, something like that. So yes, I'm going to be talking about a readily interpretable, fully convolutional autoencoder-like algorithm for unlabeled waveform analysis, which is essentially a way to say how many buzzwords can I put around pulse analysis itself. This is a sort of overview of what I'm going to go through. There are 3 key sections. I'm going to talk a bit about the background and signal processing ideas behind what we use here. Then I'm going to go through the machine learning model itself, and I'll wrap up with a main section on sort of how this model is performing in our early studies. So starting with some background and signal processing stuff. So this is a pulse. You can see, you know, there's a very simple pulse. If our pulses look like this, we'd be very, very happy. So it's very simplified. But what you have here, you have what you actually observe, the red waveform, this SI. That is basically, it contains 2 pieces. One is the actual pulse itself, which is the shape of which it will have some characteristic form given by t, and then some amplitude where that shape will just be scaled. And then you have a noise term, and here I've just put on, you know, simple white noise, but obviously the real noise model should be a much more complicated thing. This is your pulse. Now what you go away and do with this, you know, typically you get your waveforms, they'll have a pulse in there. You want to say, okay, what is the energy in my pulse? When did the pulse occur? What type of pulse was it? And now the classic way to get that information from these waveforms is to then to fit them, or maybe do some more complicated sort of process, but there's a whole bunch of different approaches that have been developed. So I'm going to add in now an additional one. And I'm going to start with the idea of fitting those waveforms. Now, if you believe that your waveform has that very simple sort of structure where it's some shape t scaled by some amplitude, and you can write down a very simple chi-square for what that fit would be. It's going to be the waveform minus that fit but scale that shape but scaled by this parameter a. And you can minimize that. You can just by differentiating it, setting it for 0, and then just by rearranging that, you get straight away a formula for the value of a. Now, what we've done, you've put your template, what the pulse you expect to get at a specific location, and you've immediately extracted the value of a. And now you can move that pulse to the next location and immediately again extract the next value of a and just repeat. And what you're doing when you do that sort of repetition is essentially convolution. So this A is the best amplitude prediction at a given location. It minimizes that chi-square. And by moving this across, you can turn that formula for A, you can see my mouse, you turn this formula for A here into a convolution, which is given by this. So at each different point, at each J, we get a value coming out of this filter F, which is just given by this equation. And this is a beautiful idea. It's a very simple idea based from the heart of the signal processing. It's called matched filter. And you can see that you get this green line where there's very little noise. You can just read off the local maxima. And just by looking for these local maxima, you can say exactly when a pulse arrived and exactly what its energy, what the corresponding energy was. One thing that's interesting, and I'll come back to it a little bit later, is if you look at this, you can see how symmetric the filter is. And this is basically pulling out what's called the autocorrelation function of the underlying pulse. So by convolving these pulses with themselves, you get this sort of symmetric shape. So this is the match filter. Now there's a challenge here, which is that if you very often in our detectors, you may have 2 pulses arrive in very short amount of time. So too short for the detector to have finished responding to the previous pulse. And so the second pulse sort of rides on the tail of that first one. Now the match filter is going to convolve these together. So you'll get the green line, and you can see, whilst you could sort of see that there were 2 pulses in the original waveform, by the time you've gone through this match filter, it's not at all obvious, and you can sort of see from this pulse here, you get a different sort of shape to what you would expect. And the downside of all this is you've missed your pulses. You wouldn't reconstruct them correctly. The amplitude you'll get out will probably be wrong. If you just read off the green here, you're never going to get the true value of the blue, and obviously the timing and so on will have changed. So a big part of what we developed here is how you can handle this. And the simple thing that you can straight away do is take a second filter now that doesn't try to recover the amplitude, it just tries to identify when the pulse occurred. So this is basically the same kind of idea. It's going to look like the rising edge of that pulse, but it's going to be very differentiating. So essentially you can sort of offset that so that half of it's below and the half is above the axis, and then convolve through. So if you do this, you get this green line, where you can sort of see now it's very easily pulling out 3 different pulses, even though in the red that's not that obvious at all, and doing a really good job of identifying when a pulse has occurred. This is obviously not getting a good amplitude. So now you can pull these things together, and here is the last slide with some of these mathy bits. So in these waveforms where you have 2 pulses, you can write down that this is what the signal will look like. You've got 2 pulses given by amplitudes A and B happening at time k and time m respectively. Now when you do the normal match filter and that normal convolution, you end up with a sort of an autocorrelation function t squared, but focused at this point k and scaled by a, and then a second one a bit later at m, but scaled by b. And if we now can identify where these pulses happen, if we can identify k and m by using what I showed on the previous slide, then we can write down the 2, we can convert this line here into a matrix equation like you see on the bottom. And this is brilliant because now we can just simply invert that matrix. Our goal is to get A and B, it's the amplitudes that we actually see. And we can get this by simply inverting this matrix and applying it to the S here. So, and this is sort of a graphical version of this, right? So you can see the green line is the match filter, the orange line is this, is the pulse finding, the pulse finder. And then when you do this inversion, you recover both the time and now also the amplitudes. So the purple dots correspond perfectly to what the true pulses were behind. And so just to wrap this up, just to summarize this is the sort of procedure you have here. You convolve with the expected signal shape. This gives you the optimal signal to noise ratio for single pulses. And then what we need to do is look for local maxima to identify when a pulse occurred, what its amplitude was. But when you have pileup involved, you can bring in a second kernel, which is just there to identify when the pulse happens. This kernel has to be much shorter, it has to be much more highly differentiating compared to the other filter. We can now recover the true amplitude by doing a sort of unfolding step where we invert the matrix of the convolved amplitudes. And then this whole process is extremely fast. There are very few steps involved, which makes it very, very simple. It's actually simple enough that I think in practice you can put this in an FPGA and do it reliably. And I think some experiments do this sort of thing without the pulse finding piece, the pilot. But there are some challenges here, right? The whole thing here has been predicated that we know what the signal shape is. And very often you will not have a good understanding. You may have some basis, you might be able to come up with a simulation, but there'll always be some sort of, some detector effects will always creep in. There'll be crosstalk, there'll be some bad termination of a cable. These sorts of effects can significantly change the kind of noise, the kind of shape that you end up with. And then the other challenge here is that there often be different types of pulses. So how we want to tackle these approaches, given the nature of this workshop, will be machine learning. And so for the next bit, I'm going to talk about how we develop these ideas into a full machine learning model. I'm going to start by giving a brief overview of autoencoders. I apologize if this is familiar to many, but just to give us all the same footing. So an autoencoder is a kind of staple in the field of unsupervised learning. So it's unsupervised because your loss function doesn't include any information about any true information, any labels. What you do is you take your input data and then you predict an output data structure that has the same structure, has the same form as the input. And so by comparing the input and the output, you can write down your loss function without actually knowing anything specific about what kind of pulse it was. Now, why this is interesting is what you do in the middle of this. The goal here is to reduce that dimensionality. So this sort of sketch here is actually it's a deep convolutional autoencoder. You can see the first layer it does a convolution. There'll be some pooling or something in between. Then you reduce the dimensionality a bit. Then you reduce it again. And finally, you flatten this out, go through some sort of fully connected layer, and you end up with 10 dimensions. So we started with an image of 28 by 28 pixels. We come down to 10 features, essentially. And then we do an inverse process where we decode that space and we get back something that looks like the original image. And so this latent space is being learned. You basically massively increase the amount of information. Well, you've preserved as much as possible the information, but you've massively reduced the dimensionality. So that's a typical autoencoder. Now, for our needs, adapting this is a little bit, there's a few things we have to think about. It's great that we can learn off unlabeled data. It means that we don't have to produce a simulation. We can just look at raw data sets. We can take calibration data or whatever and come up with these approaches. But if we just did a standard autoencoder, firstly, that sort of deep structure that I just showed, it can be difficult to interpret what's actually being learned. And that gives you, makes it a little bit harder in terms of systematics that you have to consider and so on. But also, the structure I showed before, you're reducing dimensionality. So how do you handle a situation where your waveforms are going to vary in length? So I'm going to come back to everything I sort of showed before and build up this model. So I started before by saying, we have our input waveform. In this example, it's the red line here. And like you can see there are 3 true pulses underneath it, all with the same amplitude, all spaced evenly. We do 2 convolutions. We convolve with a layer that's doing the match filter. It's trying to find the amplitude. And then a second one that starts at the input again and tries to identify when a pulse occurs. So we do a convolution, and then we have a nonlinear activation function that sort of extremizes that to help make sure that we really say exactly when the pulse happens. Now, the next step is to take these 2 outputs and multiply them together, bring them together. This will essentially mask out everything in this amplitude layer. It's everywhere there's a 0 coming through the pulse finder will now be masked out. And what we'll be left with is just a series of amplitudes, roughly amplitude information at the right location here. Then we have this unfolding step. So this is where we took that matrix and we did the matrix inversion. So again, this is something that we have to confirm this really works, but I think we're seeing that it looks reasonable. We can convolve this with another template which represents sort of that matrix, that inverted matrix. And then we apply that same extremization process to just remove anything in between when there was no pulse should have been detected. And what we get out at the end is this encoded space. And so you see 3 spikes happening at fixed distances at roughly the same amplitude, which is what we know went in. Now here we have, this is what we would like to get out, but now we have to train this somehow. And so we have a final step, which is now to convolve, to sort of convolve back the identified waveform, identified pulses, to give a waveform that looks similar to the input by basically using a reversed form of this amplitude layer. Now, a few things to say here. This is fully convolutional, so we haven't done any pooling. And this means that at each step, all we ever do is a convolution. So we can have, if our waveform varies in length for the inputs, everything will just follow through. I mentioned that we have an amplitude here. I can talk a bit why this has to be reversed, but ask me in the questions maybe. But the point here is we have to make sure that these 2 layers, we want to reuse the information between these 2 layers. So we tie these 2 layers together by through a regularization that says, make sure that this layer, when you flip this layer, on the mirror image of this layer, it doesn't look too different to the actual match filter that's being applied. And then finally, why I say this is autoencoder-like, it's not as typical autoencoder, is because what we haven't done here is like dimensionality reduction. We're defining our loss based on the difference between the input and the outputs, but we are not defining, our goal here is not to reduce dimensionality, but rather to increase sparsity. So what you have here is basically zeros everywhere, and then a spike with the right amplitude where you believe a pulse has occurred. And all of this, when you put this together, makes for a very heavily constrained model with not too many parameters. You can see here, this is the implementation we've been testing at the moment. And the main thing I want to highlight is, we have 300 parameters in this, which is relatively small, certainly compared to a deep, typical deep convolutional network. And the structure here is sort of very motivated by the physics. So this heavy constraint means that we should actually, this is how we get back the interpretability, because we know exactly what each layer is supposed to be doing. So let me now move on to sort of summarizing the performance of all this. Hopefully you've followed how the model is built. Let me try and show that it does work as we expect. So just a brief aside on the data that I'll show here. It's sort of real toy simulation. We basically feed in input waveforms where input impulses. So you have a delta function which says I had a noise, a pulse here, and then we apply some white noise on the input, and then to give our final waveform that we actually then train on, we involve this input with a pulse shape that we think is typical of a detector, and then add some white noise. You can see the formula for our pulse shapes here, and for all of this, the next few slides, all of our shaping time is 8 samples. And then in terms of what we actually put in here, we basically create waveforms with 1 or 2 pulses in the waveform. We randomize the pulse times, and that's what we train off. I should highlight that we don't use this truth information for the training. This is just so we can then validate that this is learning meaningful things, that we know this truth. Okay, so here are some examples. Here's one trained model acting on some of that toy data. And I want to highlight, bring out here is so you can see this pulse in the bottom right, for example. There are 2. There's a kink here. You can see that it's actually getting these 2 very nicely separated pulses in the end with roughly similar amplitude. You can see it here. It's much more clearly defined. And again, the fact that the second pulse is sitting on the tail of the first hasn't really affected the recovered amplitude. It's the same here as well. Now this is just some examples. Let me make this more quantitative. So in terms of the accuracy of the prediction here, how is it getting the multiplicity right? So you can see that for events where we know there's only 1 photon in there, about 99.6% of the time, I'm correctly saying there's only 1 photon in there. For events where we know there were 2, it's 64% of the time getting the 2 photons correct. And you can see here we've given a baseline model, which is just basically taking SciPy peak finder, which is a standard method in the SciPy Python package, and just run this on the raw waveform. That's our baseline, and then run that on the encoded space, this massively sparser space. And so this orange line is just the raw waveform using that peak finder, and then the blue is the higher encoded space. And so you can see how much better we're doing compared to this baseline. And then the next sort of interesting thing here is, so you can see, the question we want to answer is how well does this accuracy, how well can you reliably reconstruct 2 pulses as a function of the separation between those 2 pulses? And you can see, so remember the shaping time is about 8, so that would be about here. So once you're above that shaping time, you have pretty much close to 95 to 100% efficiency at reconstructing the 2 photons. Even below that, you're down to 5, you're actually getting 50% sort of efficiency. So 20, 30. So this is doing a very good job at pulling out 2, correctly identifying the number of photons, even at relatively short spacing. How reliably is it getting the right timing information? So to form this, we have to compare the recovered pulses to the true pulses. We do this pulse by pulse, and then you just look at the time difference. So what's important here is not the specific location of these 2 distributions. What matters is the width. And you can see that you can see the parameters in the stats box here, that the width of this algorithm is much nicer. And then a similar sort of thing for the amplitudes. So I will brush past this, but for time, you can see basically for single photons, we're not actually doing as well as the baseline, but for double, we're doing considerably better. We don't have any of this sort of funny structure. Now I mentioned interpretability, and so this is what we've actually learned. So you can see in the blue line here, you can see this pulse. The blue line here, you can see this pulse shape on the right, and then this is sort of ringing effect at the beginning. This is basically differentiating itself out, so it will not integrate away. So the main thing is you actually learn to pulse on the right. You can see that the red line is the mirror image of it, so the tying is working. The pulse finder, this orange line, has really learned to just look for a very big spike. This is actually looking for the second derivative of that leading edge, which is exactly to say where's the point of inflection in that leading edge. This is exactly what you would like to see. And then the unfolding there looks close to what I'd expect, but basically it's shifted over to the edge, whereas I would have expected it to be in the middle. And I have some ideas about why that's the case. So in short, yes, I think we can understand this. Now, there are many more details and details to the model that I haven't gone into, in particular the various regularization strengths, the various parameters behind the architecture. We have to optimize all these sorts of parameters. We have to understand how the model performs as a function of these parameters. I will
Well,
not.
since I was telling you about the time, so I don't think it makes sense to rush too quickly through things because then no one understands anything. But
Okay.
if you want to spend like a few extra minutes talking about this, feel free.
Okay.
So
I have like
you can,
I think I have 3 more slides, so I'm close to the end.
yeah. So people, well, I posted where people can post questions, but just yeah. Anyway, you can figure it out.
Okay.
I'll
Okay,
cut
so
you off after 5, regardless of what you do. So
I'll summarize here. So the 3 different sorts of regularization we have have an L1 regularization on the activation of the encoded space. So this encourages that activation to be the encoded space to be very sparse. This L2, we look at the element-wise difference between samples in the learned amplitude layers, and then apply an L2 regularization on that. This is to encourage that you learn a smooth amplitude rather than learning just a lot of noise. And then you have a time between these two, the time inverted and the original amplitude layer. So there's a parameter there that shows the strength of that time. And then, so here you can briefly see some sort of preliminary studies on the impacts of these parameters. It's a little bit, one thing we've sort of seen is that no single parameter captures the performance very well. They seem to be sort of correlated in interesting ways. One thing we have observed is the interpretability really depends how easy it is to look at those filters and say, oh, this is a pulse and this is noise and this just looks like rubbish. The main thing here is this alpha tie parameter and this derivative parameter. They play a big role in that piece of this. In terms of the stability, however, one thing we've seen is that for certain parts of this parameter space, we very often see that the model just learns nothing. It just learns a straight line, and it obviously trained itself into a place where the back propagation is no longer having an impact. And then finally, one point here is, if you're willing to relax, what I would say is the interpretability of this, you can actually get even better performance out of all this. So you can see, I didn't spend too much time on the amplitude plots before, but you can see you can really get very good amplitude performance for both the single and double photon events, the double pulse events. But then in some sense, you've lost some of the interpretability here. There's no obvious spike in that peak finder. Actually, the amplitude filter, the input amplitude there is doing more of that differentiating. The unfolding layer here looks more like I would have expected. It's symmetric and centered. And then obviously the output here does look like a pulse. So, maybe it's up for argument whether that's more interpretable or not, but this is an aspect of this model. And so that's it. Let me wrap up and then you can cut me off, Chris. So one thing I kind of wanted to draw out here is that, I think there's probably some students on the call and machine learning is not just the black box. It's actually some aspects of it are quite intuitive. And these, convolutional neural networks are essentially just these match filter ideas, but then stacking them up one on top of the other. I've walked you through this model that we've developed that takes some adaptations that we came up with of this match filter approach. The model has some quite nice properties. It's fully convolutional, so it doesn't care how long the input waveforms are. It can be trained on unlabeled data, so we can in principle learn off calibration data sets or whatever we can come up with. It's very shallow and it's heavily constrained, so it's in principle relatively easy to interpret. I say in principle, but it also has fewer parameters to learn, so we can train it more reliably. And then there are several things to do. So, stability and the repeatability. I think I highlighted this a little bit, that we seem to have a few places where we train into a bit where it stops learning. Can we solve this? We have to test this in slightly more realistic scenarios. We need to look at real data. The baseline that I've shown is very crude. It'd be nice to use a more realistic model that's close to what some experiments are doing at the moment. And there's a whole piece that I haven't touched on at all, which is how you can do sort of reuse the amplitude layers that you've learned to actually do pulse classification directly. So moving towards having different types of pulses and using one algorithm that can learn in the same way, different types of pulses at the same time. So I will wrap up there and happy to take questions, and apologies that I overran a bit.
Okay, so going through Slido, it seems like the top question right now, why is the encoded curve displaced with respect to the raw shape?
Ooh, that's a nice question. It's to do with, so there's some degeneracy. There's a few places in the model where it's got some degeneracy. Let me see if I can find. It's sort of to do with this actually. I mean, the pulse finding filter here, this orange line, it's not a full length as the amplitude one. It stops at 90. But in principle, the you could learn to find this sort of spike anywhere within this filter. Oh, I'm sorry. Do you want me to share, Chris, the question?
Oh, not right. Sorry to interrupt. Yeah. If you can share them just when we look at them.
Okay.
Just so people can, otherwise, it's just good to have it read aloud. But anyway, you have to look at your plot now. So sorry.
Yeah. But yeah, so the point is you can sort of learn this spike anywhere within that pulse finder, and that will just amount to an offset. And I think it's sort of the same thing that's going on with this unfolding layer as well. You can see it's sort of learned itself into this edge. We actually have in the model itself, you can see this offset layer. So basically we have a layer already kind of helping that allows us to encourage the pulse finders to be centered on the rising edge of the learned pulse. We haven't actually included such a layer yet on the unfolding side. So it's one of the subtleties of this that when I built, the very theoretical model at the start, we didn't expect. But I hope that answers the question. Yeah.
Okay. We have another question from, well, not really a question from Chris. I think what you're doing is compressive sensing, but without a requirement on sparse latent space. Dictionary learning helps when pulse shape is unknown.
Maybe I'll clarify just a bit. So I was just wondering if you looked at any like engineering literature, signal processing or whatnot, to see what others had done, because this reminded me a lot of something I'd seen called compressive sensing, where it's like an active area of research, but even things like unknown pulse shapes, they have ways of dealing with this. So I was just wondering was it wanting to play with autoencoders as a way of doing this, or was it like there was some need that other methods weren't hitting?
So my in on this,
all of that.
So I mean, I haven't heard of compressive sensing, so this is great. I'll go away and look that up. I started with this from actually not from the machine learning side at all. I started from the match filter sort of ideas, and we wanted to apply this. Actually, my PhD experiment, we wanted to apply this. We were doing we were fitting in-root templates to the waveform, and it was just very slow. Many waveforms would just fail. It was, and how you got that template as well was tricky. We were doing sort of pulse averaging and so on. So I spent some time doing the signal processing side, looking at match filter and so on. We had these problems with pileup, so I developed this pileup idea and so on. But it was very clear as I was going through this that actually this is mapped perfectly to convolutional neural networks. So how can we develop this into an algorithm? I haven't seen anything that looks like this sort of autoencoder-like, very relatively shallow structure. But these things that you point out here, I'm not familiar. I know dictionary learning, and that could be. So I've got some ideas for where for the next step with that. But compressive sensing, I don't know. So thanks for the heads up.
Okay, I think we have time for just one more question from Igor. Did you try the algorithm on waveforms with non-white correlated noise, which some experiments have to deal with?
Yeah, it's a good question. So our noise model here is not pure white noise. We have white noise on the input. We then convolve that with the response time of the detector, the pulse, and then we apply additional white noise. So we've tried to make it, within this sort of toy data, relatively realistic, but I appreciate, more serious artifacts like nonlinear ringing, after pulsing, whatever. That's the sort of thing I'd like to get. My sort of next goal is to get hands on some sort of test stand data and run through with that. That answers the question.
We do, Chris is the chair, so he can comment, but we do have a little bit of stretch time in the agenda. So I think we could cover one more question.
I want to make a comment if I can. It's not even a question. It's just something that struck me in what Ben said, that apparently interpretability is reversely correlated with performance, which I guess to some extent is expected, right, of these deep learning models. So anyway.
Yeah, I wasn't expecting that, but it does seem, basically you give the model more flexibility and it goes away and learns, it can perform better. I think where I would like to preserve interpretability is probably in terms of the systematics, because if you can interpret what you're getting, then you can much more easily, you can be more confident that it's not going to be it's not good enough to learn something in your simulation or in your calibration data, for example, and then doesn't make sense elsewhere. So that's where I think interpretability is an interesting thing, but it'd be nice to be able to quantify interpretability in some better way. And it is so far interesting that we have seen some, giving it more flexibility means better performance, but poorer interpretability. Should we move? Should I take this question? Or,
yeah, then why don't you take that question while we make sure the next speaker is ready to go?
Okay. Yeah, okay. My goal with this is replacing hit finding. So a more advanced way of doing hit finding where we can learn this directly on this. Partly, even if you don't do the learning piece of this approach to doing the reconstruction itself, if you know what the waveform looks like and so on, is going to be very, it's very, very quick, and it's actually very reliable. So if you know already what the template will be, you can just give those weights to the, sure, you can use TensorFlow or whatever, give them those weights and just do the convolution. And so then this is part of my goal, to begin with, is give it a structure where we know works, but then we can actually use this to learn it as well. And so I've been on experiments where they've done very elaborate things to learn what that template looks like. This is better because it's a sparse representation as well. It does mean you could do data reduction on that as well. And then it leads into the next piece of this work, which will now be using this encoded space with the pulse classification that we've got to then do probably something like an LSTM on the varying input encoded spaces. So that's where like, I don't know. Feel free to ask me more if that doesn't answer the question fully, but that's where I'm from.